Today's lesson is building on some information that we've already studied. We're talking about the gravitational force near the Earth. So, scientists wanted to explore the nature of gravity. And what they did was they measured the force of gravity acting on various masses near the Earth. And they found the forces acting on these various masses, and they plotted the data. So that seems like a scientific thing to do, plot the data of mass versus the force of gravity. And they found that the larger the mass, the larger the force of gravity. It was kind of expected. They said, what else can we do with this information? Well, how about we take the slope of this graph? It was a straight line linear relationship. The next logical step for a scientist is to find the slope of a straight line. They determined that the slope, which is equal to rise over run, from this graph between these 2 points, (80.1 newtons down divided by 8.14 kilograms. Bear with the numbers that they've chosen here for the rise and the run. Punch this into your calculator, and what do you get? The slope of the force of gravity versus mass graph. So the answer is, to two significant digits, 9.8 newtons per kilogram down. This value, we give the little symbol G. Now some of you have been using the term gravity to describe this little G with the arrowhead on top. But that's a misnomer. That's not the correct name. The correct name for this term is the gravitational field intensity. Gravitational field intensity is the force per unit mass acting on an object when placed in a gravitational field. So when you do this experiment on Earth, G is 9.8 newtons per kilogram down. But if you did this experiment on the moon, you would get a different force per unit mass. Why would you get a different force per unit mass on the moon? Can anyone think of a major difference between the moon and the Earth that would result in a lower gravitational field intensity? In fact, it's almost 10 times less. The gravitational field intensity on the moon is 1.6 newtons per kilogram. So there is gravity on the moon. When you jump up on the moon, you fall back down. When you throw a ball up in the air on the moon, it comes back down. But its rate of acceleration is a lot slower than it is on Earth because its gravitational field intensity is 1.6, almost 10 times smaller than it is on Earth. The main reason why it's smaller is because the moon has a very small mass compared to the Earth. The Earth is a lot more massive. So the bigger the mass, the bigger of the planet or the satellite, the larger the gravitational field intensity. We have an equation that says force of gravity is equal to mass times the gravitational field intensity. Please distinguish between the terms in this equation. Force of gravity, mass, gravitational field intensity. Got it? It's a vector quantity, g. And it varies slightly with altitude and latitude. So we discussed why the acceleration due to gravity is affected by altitude and latitude. And for both of these, it's because you're farther from the center of the Earth. Whenever you're farther from the center of the Earth, the force of gravity is smaller. So you'll experience a smaller force. Objects will accelerate downward at a smaller rate. And the gravitational field intensity varies with altitude and latitude. Same with the moon. The farther you are from the center of the moon, the smaller the gravitational field intensity is. So you can actually get a question about free fall kinematics on the moon now. Instead of putting the acceleration due to gravity equals 9.8, what would you put for the acceleration due to gravity on the moon? 1.6. Okay? That would be a good kind of making connections or thinking question, where you've taken something that you've done and have been doing on this planet, and you're doing the calculations for another planet. All right, the next concept is clearing up a very large misconception that people have in science. And that is the difference between mass and weight. We've been using these terms interchangeably outside of science, but in science they have vastly different definitions. Mass is defined as the amount of matter in an object. The unit is a kilogram, and your mass is the same whether you are on Earth or on the moon. If you weigh 70 kilograms here, your mass will be 70 kilograms there. Got it? So mass does not change whether you're on Earth or on the moon. So the mass of an object remains the same whether or not the measurement was made on Earth the moon, or any other planet. Even if you are in outer space, your mass does not change. So if you take a 50 kilogram object on Earth and you bring it to the moon, it's still a 50 kilogram object. If you take that 50 kilogram object and bring it to outer space, it's still a 50 kilogram object. However, you'll observe differences. What are the differences that you will observe? What changes? If your mass is not changing, what is changing? Because there are obvious differences between objects on Earth and objects in outer space. Ellie?
Your force. Your force of gravity is different.
Your force of gravity is changing, and it's different. So your force of gravity is greater on Earth than it is on the moon. And if you're in outer space, your force of gravity is 0. So the force of gravity is defined as the force of attraction. Sorry, can't see. Thank you. Between any two masses in the universe. So on Earth, it's the force of attraction between you and the big Earth. On the moon, it's the force of attraction between you and the smaller moon. But in outer space, there's no other object. You're in space. So there's no force of attraction. Therefore, there's no gravity. This brings us to the next term, which is weight. Weight is defined as the force of gravity that a celestial body such as Earth, such as is 2 words, the moon, exerts onto a mass. The equation for weight is, therefore, does this look familiar? The equation for weight is the equation for Ellie? Gravity. Calculating your weight is the same thing as calculating the force of gravity acting on your mass. So your weight is not measured in kilograms or in the imperial system in pounds. Your weight is measured in newtons. So we've been using this term to express our weight, yet we express our weight in units that correlate to mass. Whenever you're talking about your weight, you're talking about your mass. So we have to correct that. Weight is the force of gravity that a celestial body, such as Earth or the moon, exerts onto an object. And we calculate our weight using this formula. The force of gravity between an object and a planet depends on the mass of the planet, the mass of the object, the distance between the two, so the larger the mass, the larger the force of gravity. The larger the distance, the smaller the force of gravity. Let's take a look at sample problem number 1. A 50-kilogram person is standing on a bathroom scale inside an elevator. The scale is calibrated in newtons. What is the reading on the scale when the elevator is accelerating up at 2.2 meters per second squared? First of all, tell me what sensation you would experience if you're in an elevator that is accelerating upward. What do you feel? And keep in mind the opposite situation. The sensation you feel when an elevator is accelerating downward? When the elevator is accelerating upward, what would you experience? You feel like you're being pushed into the floor. So if you're pushing onto the floor with a greater force than you would normally, then the floor is going to push up onto you with a greater force than it would normally push. So imagine if you were standing on a scale while accelerating upward. As you're accelerating upward, the scale's measurement should go up because you're pushing down on the floor with a greater force. The reading is going to go up, or the scale measurement will go up. All right? So the opposite is true if you're accelerating downward. What's the sensation you feel when you're accelerating downward? Who can describe it? I know for myself, it feels like my stomach is traveling upwards. But the sensation that your feet would feel, you feel lighter. So if you were standing on a scale while accelerating downward, the scale would actually decrease. And this happens. Take a scale into an elevator. Find a random apartment building, bring a scale into the elevator, and try this out. It'll work. So this question asks you to set up the situation. A 50-kilogram person is standing on a bathroom scale inside the elevator. The scale is calibrated in newtons. What is the reading on the scale when the elevator is accelerating up at 2.2 meters per second squared? So we have a person standing on an elevator, standing in an elevator rather. The force of gravity is pushing down. Since this person is resting on a scale on the surface of the elevator, what force will be acting up? Good, the normal force. Now the normal force, you're going to actually, it will be the same thing as what is read off the scale. Because the harder you push down, the harder it's going to push up, and the scale reading will increase. Since we're traveling upward, let's make upward positive. If that's the case, let's follow the same two steps that we've always followed to answer this question. List all the forces indicating the direction with plus or minus signs acting on this person. So net force equals, what would we say? So up is positive, we will say normal force minus gravity. Why minus gravity? Because gravity is in the opposite direction. Next step. What's my next step in answering this question and the second step for answering all Newton's law questions? Good. So MA is equal to the normal force minus, what can I replace gravity with? Do we have an equation for gravity? What's the equation for gravity?
The force Fg equals mg.
Perfect. In this question, they want us to find the reading on the scale while this object is accelerating. So the reading on the scale is going to be equal to the normal force. So solve this for the normal force. That means we're bringing negative mg over the equal sign. When we do, we have ma plus mg. At this point, we're going to sub and solve. We have 50 kilograms times an acceleration of 2.2 newtons per kilogram. Now I know the question expressed the acceleration in meters per second squared, but it makes more sense for me to use the units newtons per kilogram in this equation because the kilograms will cancel out. Keep in mind that these two units are interchangeable and use that. Use the appropriate unit whenever necessary. Plus 50 kilograms times 9.8 newtons per kilogram. When you bring this negative over the equal sign, it becomes positive. Punch this into your calculator and tell me what you get. Should get 110 newtons plus 490 newtons which is a normal force of 600 newtons. Sample problem number 2. A 60 kilogram person is standing on a bathroom scale calibrated in newtons. A friend pushes down on the person with a force of 70 newtons. What is the reading on the scale? So, let's break this down with a simple free body diagram first. Please make sure that you put a happy face so that when you're studying and reviewing, you know that physics is a happy experience. What forces are acting down on this individual? Selena?
Force of gravity.
Good, that's one.
And force applied.
The force applied by who?
Friend.
Your creepy friend who is applying a force while you're standing on a bathroom scale. So, there's going to be an upward force as well, hopefully. Otherwise, you'd be falling through the bathroom. And that upward force is going to be the normal force. Since you're standing on a scale, conveniently, this normal force can be read by the scale. What we want to find is what is the reading on the scale. So what is the normal force? So let's set up this equation by following the 2 steps. List all the forces acting. So we have the force of gravity plus the force applied minus the normal force. So gravity and your person, your friend, are going to be pushing down, and the normal force is in the opposite direction. Now, what's the next step? Rena, what would you say the next automatic step is? Good. Change F net into MA. But this question is different from ones that we've done. And it's different because this object is not accelerating. This object is at rest. Your buddy's pushing down on you while you're standing on a scale, but you're ultimately at rest. If you're at rest, what do you put in for net force? We don't put MA. We replace net force, but not with MA. If your acceleration is 0, what would you put in? 0. So 0 equals gravity plus force applied minus normal force. So your job is to determine what the normal force is. The normal force is equal to gravity plus the force applied. And if you think about this, what is the scale going to read? Is it going to read just your weight, the force of gravity? No. It's going to read your weight, which is the force of gravity, plus the force that your buddy is pushing down on you with. That's what the scale is going to read. Make sense? So, mg plus 72.0 newtons, that's 60.0 kilograms times 9.8 newtons per kilogram, plus 72.0 newtons. Punch this into your calculator. 60.0 times 9.8. Give me your answer to 2 sig digs plus 72 newtons. What's 60 times 9.8 to 2 sig digs? Carmelo?
I got 588.
588?
Yeah.
So the 2 sig digs would be 590? Plus 72.0 newtons. No decimal place and 1 decimal place. Give your final answer to no decimal places. $590 plus 72 to no decimal places. 660 newtons. So the normal force that's applied is 660 newtons. Got it? So this question is really different. And the reason why it's different is because of this. This is the first time, instead of putting the net force is equal to MA, that we've put the net force is equal to 0. Got it?